Hello. We are here for 9.1. This is our first of our flipped lessons for Unit 9. We are looking at our parts of circles. Again, this is the first official lesson. Previously, that was a trial, a warm-up, a practice. This is now our first official. So we're going to jump right into it. We are on page 1 of our note packet, and we have a list of terms. A center column for meanings, and a column full of circles for examples. So this is a time for us to understand these terms. If vocabulary is one of your challenges and you are forced to see terms you are not familiar with, this is a great way of taking these and turning them into some note cards or flashcards. And I'm more than happy to help provide you with some if you feel that will be useful. Now, many of these will be the same things you can see in some of your Delta Math, but I have adapted a few of these. So let's jump right in. Now, the first term is our center. Now, our center of a circle is something that most of us can kind of figure out. It is a point that is equidistant meaning the same distance from any point on a given circle. Now, and the way we think of that, it is right there in the middle. Now here, I'm not being super precise, I just picked a point in the middle somewhere, but if I were to be precise, thinking of how to use maybe a compass, and that's why our compasses work for drawing circles, is we place a center point, that's usually where our needle goes, the pencil part makes the radius, and then if we go around, everything should be exactly the same distance. Now, because our tools are not perfect, it doesn't always work out well for us, but it happens. Now, our center being a point will usually be labeled with a letter. So let's go ahead and call this A. And what we would do is if we're asked to name just the center, that's point A. But if we're asked to name the circle, we name the circle based off of the center, and we call it circle A. And that's a symbol, like a circle with a dot in it, with that center point. So that's the difference between the point A, which is just A, and circle A. The circle symbol before A means we're naming the circle. Just A means we're only naming the point. The next two, radius and diameter, are terms you should have been hearing for years. I don't know when these first get introduced to you, but I am aware that at least my 7th graders have used these before, and that wasn't the first year that they've been introduced to them. So by the time you're in 9th, 10th, 11th grade, as most of you are, you should be very familiar with radius and diameter. We've also mentioned these a couple times prior in the year. Now, our radius is a line segment that runs from a circle's center to a point on the given circle. So when we say it's on the given circle, we're talking about something on that circle's circumference. So if I take a point in that center, if we're still looking at maybe center A, maybe this is a different circle, a radius is just from that center towards the outside. Now, every circle has an infinite number of radii. Radii is the plural, so I go to turn my paper. And radii is just like that. It's rad with 2 eyes. Now, within the same circle, every radius is the same. Again, that's why our compass works. We set the radius with our compass, and as long as we don't shift the size of our compass, it should keep that constant flow as we go around the circle, keeping everything the same. Again, since our radius is a segment, if we know the endpoints and we're asked to name it, we would name it as a segment. So if this was A and this would B, our radius would be segment AB. And we still use that segment bar above it. And I'm going to do my best to try to pick this up a bit. I know I tend to overtalk and go too slow for some of you, and the beauty, I hope, of this being flipped is that if I'm going too slow for you, you can speed it up, and if I am going too fast for you, you can slow it down or rewatch. Again, our diameter here. Diameter is another one you're very familiar with. It is another segment or line segment. I'm just going to stick with segment that runs through a circle center. Okay, we're going to put our center in there, but it's going to pass from one side of the circle to the other. So again, if this is center A, this is point B, maybe this is point C, our diameter is a segment, so we're going to name it by its endpoints and put a bar over it. So it does have that in common with the radius. The difference is this goes from from one point of the circle to another point on the circle, passing through the center. What's different now with the next one is a chord. A chord is a segment. Now this one could have also been chord. And I honestly don't remember which one Delta Math puts, so I'm going to put both there as interchangeable. A segment that connects any 2 points on a given circle. And the reason I came back up to diameter and said that could be a chord, our diameter fits the description of a chord. It connects any 2 points on a given circle. What makes the diameter special is that it runs through the circle center. A chord on its own does not have to. Again, if this is circle A and that's the center, I can have chord EF. It is a perfectly fine chord, but it is not a diameter like CV was before. It's still a chord because it's connecting 2 points on the circle, E and F, but it is not passing through point A. So those are mostly our segments. Now we're going to move on into some angles. So we have two kinds of angles. We have a central angle. A central angle is an angle whose vertex is a given circle's center. Again, if we have center A, that's going to be the vertex, and its sides or legs intersect. So that's essentially an angle whose two sides are radii of our circle. So we have an R and an R, and our vertex is that center. This is a central angle. That could be like our measure theta, maybe. You don't have to fill in all that extra, but that's what a central angle looks like. Now, an inscribed angle, on the other hand, is an angle whose vertex lies on the given circle and whose legs or sides intersect the circle at two other points. So what this means is that it's an angle that is formed by two chords. So here we have a chord and we have another chord. That vertex is on the circle. Our center is just somewhere right out here in the middle of our angle. So this is the main difference between a central angle, vertex at the center, inscribed angle, the vertex is on the circle. Now the next two, again, are lines. We started with our center, which was just a point. We moved into segments. Then we moved into angles. So let's call this angle A because that's its vertex. I'm not even going to put a point at this one, but you can if you would like. And now a secant, there's nothing for us to add here. It's a line, a ray, or a segment. We usually say line. We focus on line mostly, but it can be a ray or a segment that intersects a given circle at more than one point. Now, the reason we say it can be a segment, but we don't usually focus on the segment, is because it will extend beyond the circle at least one point. So it's a lot like our chord. If I start with a chord, like I did before, EF, so there was point E and there was point F. Now, to be a secant, at least one side has to extend a little bit. So if this was EF and I extended this just to maybe a point G, but it was still a segment, then it is now no longer a chord, it's a secant because it has left the circle. If I turn that into a ray, it is a secant because part of it has left the circle. And if both ends extend, it is a secant line, and that's most of what we're looking at. So we take a chord and we extend at least one end of it beyond the circle, and that's how we get a secant. So that is our main difference. Now, previously, I specified that our difference between a secant and a chord in your first activity was a difference between a chord as a segment, a secant as a line, and that is the main difference. Again, a secant could be a segment. It just has to go beyond the circle. Now, our tangent, please do not get confused with the tangent in our trig. It is the same word, but they mean different things, at least for our purposes at this point in time. Now, secant is another trigonometry word, but it's not one we had to deal with. But again, if you're taking pre-calculus in the future, you will probably see that come back up. Now, a tangent, when we're talking about circles, is a line, ray, or segment that intersects our given circle at exactly one point. And this is whether it's been extended or not. So what that means, if I have this one point right here and I just have this little segment coming off of it, that's a tangent segment. If I turn it into a ray, that's a tangent ray. If it goes off both ways, it's a tangent line. As long as it still only touches the circle in that one point, it is tangent. And that brings us to this last term. The point at which a tangent line intersects or touches a given circle is called the point of tangency. It should be a single point. So this is our point of tangency. That is where they intersect. A lot of vocabulary right at you. Again, I hope that most of it's simple enough that you can go right through. If not, flashcards will be helpful. Coming back and reviewing this frequently will be helpful. Sketching those pictures will be helpful. We only have a few weeks until finals, and this vocabulary is a large basis of this unit. So get the vocabulary down, whatever it takes for you to get the vocabulary down. Now, on to page 2. The first chunk of your first assignment is identifying these parts. So, my highlighting doesn't always come through the best when I print. That's why we have the videos to follow. So here, the first section that was highlighted was from G to T. And we are asked to identify the highlighted part of circle O or P as shown in each problem. And it does say to use the assignment to help you, so if you are looking at the assignment while trying to watch this video, or if you have peeked ahead at the assignment, you can use the videos and the help tools to help you. But ideally, you're watching this. So if I look at just that segment GT, first of all, I know it's a segment. So I don't typically want to go with any of those that are tangents or secants, because those are usually going to be lines or rays. And it's not going to be one of the angles. It's not going to be a central angle or an inscribed angle, because it's not an angle. Again, go back to process of elimination if you're not sure. Our segments were radius, diameter, and chord. Now, radius and diameter both needed our center. Our center is O. This segment does not touch that center. That makes this a chord. So segment GT is a chord. And we're going to kind of keep that up here. On this next one, they have highlighted just that point. Again, we've had 2 points that we've talked about. Our points were the center or the point of tangency. P is how they named one of these circles. We name our circles off of the center. So P is a center. And here, if we get down to the third one, that's shaded here. This represents an angle. In our 2 angles, we had central angle and we had inscribed angle. And central angles contain a center point. Inscribed angles, the vertex is on the circumference of the circle. So here, that's our vertex, O. O, we need to decide, is that the center of a circle or is it on the circumference of the circle? Well, we're told that our circles are O and P. They're named after their centers. So O is definitely a center, which tells me that this angle VOK or KOV is a central angle. And now there's plenty of other options in these pictures. So if you want to run through a few more of these, if you're struggling, and I can double check or change some colors around and help you with those as well. There's not a whole lot more I want to spend this time with, because some of you are going to pick this up very quickly. Now, our last one here is going to look at these tangents. So which of the lines or segments below is tangent to circle O? So again, we have to decide which circle is circle O. That's one with point O in its center. So in our centers, we have O and we have P. It means I'm looking at the circle only. Again, if you need to, cross that one off. We don't care about circle P for this question. We're not looking for one that's tangent to circle P. And tangent means it touches in only one place. It cannot go in. Okay, when it says even if extended, it means if I look at a radius here, and my radius only touches at point N. But when my definition says if extended, it means if I extend this through, it becomes a diameter. That's when it's a chord and it's touched in 2 places. And if I continue to extend my diameter, it becomes a secant. It can't be a tangent if I can turn it into a secant. So think about it in that sense. Tangents, we cannot have them curve, turn, flip, extend, shrink. They have to only ever touch, no matter what, in one place. So my radii can never be tangents. So this one's not tangent, that one's not tangent. Now if I look at H and F, well, the segment HF is a chord that touches in 2 places. The line or rays that contain H and F are secants, so that can't work. The only other point I really have anything to do with is N. And N is on this line NW, and it looks like NW only touches circle O at point N, which is a point of tangency. So NW is the line that is tangent to circle O. Now there's just a little bit left in this. There's not a lot that goes into the assignment, but may show up in some of our in-class practice. And that's how these relate to each other, how circles relate to each other in the same plane. So coplanar circles. We spent some time on the previous page looking at how different lines, rays, and segments may intersect with our circles, but what about circles intersecting with each other? So we have different situations that can occur. Now, we can have circles that overlap like they do here. This one reminds me of certain bubbles I would blow growing up. Sometimes they'd make neat intersections. And in this case, if they overlap like this is also an example of maybe Venn diagrams. They have 2 points of intersection. There is some overlap. Not a problem. None of these are a problem. They're just showing you the different relationships. Then we could have 1 point of intersection. And when there's 1 point of intersection, we call these tangent circles. Because instead of having a line that's tangent to our circle, we have another circle tangent. You may also want to think of these as like kissing circles. We can think of this as like a mommy circle kissing a baby circle. Maybe that's a little silly, I don't know, but whatever helps. They only ever touch there. And this one, we've got one inside of another. Again, if we think of blowing bubbles, maybe you have seen this happen when you've blown bubbles in the past. You've had a little baby bubble show up inside of a bigger bubble, and maybe they have 1 point where they touch. Maybe that's where your wand was. That is 1 point of tangency. And then it is also possible for there to be absolutely 0 intersection, whether they don't touch at all because they're just in completely different parts of the plane. This could be like dumping out your coins to count. If I dump mine out to count, some of mine are overlapping and touching, but if I separate them, these 3 coins are now coplanar. They're all on the same plane, but they are not intersecting with each other at all. There's no touching. So, no points of intersection, but they're still coplanar. Absolutely acceptable and possible. Now, and concentric circles are other ones that we will occasionally deal with, and we see a lot in the real world. Our concentric circles may appear a lot in things like bullseyes. If you're ever going to the shooting range, if you ever do archery, maybe you play darts. Another one of this, if you took like a top-down view of old stacking toys when you were a toddler and you're learning all of your fine motor skills. Concentric circles show up that way. They will have no points of intersection, but what's special about them is they share the same center. Now we will see an example below that they don't have to be concentric to still have no points of intersection and have one inside of another. But it's one of those neat things that happens. So here, coplanar circles that intersect in 1 point are called tangent circles. Coplanar circles with a common center are called concentric. So, circles. And a line or segment that is tangent to 2 coplanar circles is called a common tangent. That means it's a tangent that is in common to both circles. And so these tangents up here, these tangent lines, are common tangents. The lines are tangent to both circles. So, and that's what these examples at the bottom are going to be. We're looking for how many common tangents do each pair of circles have. No, the first thing is that if we have concentric circles will not have common tangents. So that is, if you recognize concentric circles, you're not going to have common tangents. But A is one that might try to throw you off. These are not concentric circles. Does that mean they would have a common tangent? Not necessarily. If they're not concentric, we have to see what else connects. And there's a few ways you can do this depending on your strengths and weaknesses, your skills, and your visual abilities. So, I've got this tiny strip of like pink duct tape I'm going to use here. So I'm taking this smaller circle. You can barely see just the tiniest piece of this circle coming out. And if I continue to rotate this around the smaller circle, I'm going to be crossing through that bigger circle in two places at every single point that I rotate this. And even as I get blurry on my screen, you can kind of see how that's happening. Every time I turn this around and show even just the tiniest bit of that circle under there, it's still crossing the second or larger circle in two places. So if you need a physical, hands-on way of checking, grab you a little something short, a small piece of ruler, a popsicle stick, a piece of index card, something straight that you can use to work around a circle. In this case, there are 0, forgot how to spell it, common tangents. Now, again, if I do the same concept going around the big circle, I'm never going to get inside to the little one. That's how I know there's 0 common tangents. Now on B, this one's going to look a lot like right here. Their common tangent is where the two of them touch. We're just going to we're not going to do this perfectly. We just kind of sketch a line where they touch. There are ways of constructing this. We've done enough constructions this year. I'm not going to worry about doing those. However, if constructions were something you enjoyed and you would like to do a couple constructions, let me know. I might consider that as like an extra credit thing. And then where they get a little bit different, we don't have these pictured. These no points of intersection. I told you concentric circles don't have any. They didn't draw any of the common tangents on the 2 points of intersection or the no points of intersection. On these, we do sometimes have common tangents. So that's what this last one's going to be. And here again, we've got to get kind of interesting or think about it in different ways. If I turn it a little bit like this, if I think about these almost as a side view of tires or bicycle tires, my common tangent could be the road. If they're both touching the road at exactly 1 point when it's on the road. That's my first common tangent. Grab my straight edge. To do this is still not perfect, but as close to perfect as I can get without constructing. So there's one common tangent. Now again, as these turn, there's going to continue to be one common tangent every time they hit the road. But, say we sandwiched them. There's no top here. We're going to put it between, maybe these are barrels now on their side. And we're going to put them between 2 sheets of plywood because we're being silly for some reason. Maybe we're trying to balance on it. We have a common tangent along the top as well. That one's not as neat as the bottom, but still pretty close. Top and bottom each have a common tangent. But here's the thing with these. There's more. Because there is a gap between these circles, we actually have some common tangents that go through like this. Again, this would be almost like, I might be showing my age. If you've seen old films where they do the projector wheels for films, or even an old tape recorder, that didn't match up as nicely as I'd want, there's going to be a tangent to each of them about here. And there's going to be one going the other way. Now let's see if I can get this one a little bit better. Maybe. This particular set of circles has 4 common tangents. Now out here, we can still get more tangents to this circle and more to this one, but no longer common tangents. So each individual circle has an infinite number of tangents. And that's why we're not going to ask you to do all of the tangents of one circle. That's too much. But common tangents, now we're narrowing it down. We don't have as many to go through. We finished that. We had one common tangent on this one. So we're asked to determine or tell how many they each had and draw them if they exist. So there we have them. And you'll have some assignments, we'll have some in-class work and some activities to follow these up. But as always, ask questions. This is the time to understand. This, along with our last test, is going to be a large majority of your final exam. So if you're falling behind, ask, ask, ask.